Well, students, today in this session, we will be discussing about the fluids concept. So let us go through the mechanical properties of fluids. So this chapter starts with the concept of pressure. So pressure will be equal to force per unit area, and it is supposed to be a scalar quantity. Its unit is Newton per meter square. Other unit is Pascal. So 1 Pascal equals to 1 Newton per meter square, and 1 atmosphere is the practical unit. So it will be 0.13 into 10 raised to 5 Pascals. So other practical units or larger units of pressure are bar, torr. So bar will be equal to 10 raised to 5 Pascal. 1 torr will be equal to 133.28 Pascals. And 1 atmosphere will be equal to 76 cm of Hg and 760 mm of Hg, mercury. So thrust, it is the total force acting on the surface of the liquid by the liquid in is called thrust of the liquid. Here, pressure at the bottom or due to liquid column will be given by P minus PA equals to rho GH. So PA is supposed to be the atmosphere pressure here, and P is supposed to be the difference between PE and PA is called as gauge pressure here. The pressure difference between 2 points. So the pressure difference between 2 points which are at different horizontal level is given by P2 minus P1, which is equal to rho GH, and P2 is greater than P1, and P2 minus P1 will be equal to rho GH. So this is how the equation will be. So pressure difference between 2 points, again it is the same quantity here. So it will be P2 minus P1 equals to rho GH. Then P equals to P naught plus rho GH. So different cases we are having, so we are calculating it. So P equals to P naught plus rho GH. PB minus PA will be equal to, in second diagram, A, B, C are 3 points here. So PA by PB minus PA will be equal to rho GH, and PC minus PB equals to 0, because there the height H is 0. PC and PB, that is pressure at C and D, are, since C and B are at the same level, so there will not be difference between the pressure, so hence it will be 0. In the third diagram, again it will be PB minus PA equals to rho GH, and PC minus PB equals to L rho A. So L is the distance now here. So in that case, this is how we will be calculating it. LC minus LB it will be. So that is accelerated fluid. So it's stationary fluid and accelerated fluid. So then there will be pressure acting due to them. Then tan theta will be equal to A by G, which is equal to 2H by L. So this is another equation to calculate it. So these are used for numerical purposes. Pascal's law states that its effect on the, if the gravity is neglected, then the pressure at every point of a liquid at the same height will be equal, or it will be same. So that is how we can get to go through the Pascal's law. So hydraulic lift and hydraulic say brake are the two examples for the applications of Pascal's law. So hydraulic lift, it has been discussed here. So W by A. So one side the area will be less, the other side area will be more. Then the tank is filled with an incompressible fluid. So then what will happen is W by A will be equal to F by A plus rho GH. The equilibrium of different liquids in a U tube we can calculate. So PA equals to PB, P naught plus rho GH1, rho 1 G1, rho 1 GH1, and P naught plus rho 2 GH2. If you calculate it, so pressures will be equal. So then it will be rho 1 H1 and H1G will be equal to rho 2 H2G. Similarly, here tan theta will be equal to A by G, which is equal to H by O. So these type of equations are used largely in the numericals to solve the numericals in fluids. Now buoyancy, when a whole body is immersed partially or completely in a fluid, then it experiences a loss of weight due to upward thrust. So then we call this force as upthrust or buoyant force. Now Archimedes principle, it states that when a solid body is immersed wholly or partially in a liquid, then there is some apparent loss in its weight, and this loss of weight is equal to the weight of the liquid displaced by the body. So this is how Archimedes principle will be. And then buoyant force, we can calculate it. The upward force will be equal to rho GB, that is loss of weight, where V is the volume, which is equal to H into A. So now here, case 1, sigma is less than rho. In that case, V is the volume of the body. So we get the body will float in the liquid with some part inside and remaining part outside. So this is the case. So then V1, Vi divided by V equals to sigma divided by rho. V naught by V equals to rho minus sigma divided by rho. So sigma will be equal to rho, second case. So there V naught will be 0. So body floats completely immersed in liquid. So then case 3, sigma is greater than rho. So for figure 1, R is normal reaction between the body and the bottom of the container, and R will be equal to V sigma G minus V rho G. So this is the equation which we get here. Then further hydrodynamics. So we consider here as say motion of the fluid. So streamline flow, turbulent flow, there are two types of flow. So if the velocity of the fluid of all the particles at a given point is same, so then we say it as a streamline flow. If it is unsteady, then we call it as irregular flow or turbulent flow. So then comes the equation of continuity, which gives us the relation between the area of cross section and velocity of the fluid. So it says us that area of cross section is inversely proportional to the velocity of the fluid. More the area, less will be the velocity. and less the area, more will be the velocity. So hence A1 V1 will be equal to A2 V2, or V is proportional to 1 by A. Now energy of the fluid, there are three different types of energy. One is potential energy given by mgh, kinetic energy which is given by mv square, half mv square, and then pressure energy which will be given by mp by rho. So energy heads if we take, so we are having gravitational head h, velocity head v square by 2g, and pressure head v divided by rho g. So then Bernoulli's theorem will come into picture, which says that the sum of pressure energy, potential energy, and kinetic energy for an ideal fluid is always a constant. And then we take this as a velocity or pressure head and the velocity head and the elevation. So the equations will be P plus half rho v square plus rho g y equals to constant. Now here a person is standing close to the moving train may pull towards the train because the air which is in contact with the train also move with large velocity. As a result, the pressure of the air decreases. Due to the pressure difference, the person may be pulled towards the train. Now blowing of roots by strong winds is due to this Bernoulli's principle. So during a tornado, when a high speed wind blows over a straw, it creates a low pressure. The pressure blow of the roof is high and it will lift the roof up. So because of which it will be blown off by the wind. So Bernoulli's theorem is the principle which is used here. Now application of Bernoulli's theorem, we are having first equation, that is the value of Q. Q is the rate of flow of fluid. It is area into velocity is given in different cases here. So it will be Q equals to A1 E2 divided by 2 into P1 minus P2 divided by rho into A1 square minus A2 square. So this is for the first case. Second case is Venturi meter. So either Q will be equal to A1 E2 into root of 2G H1 minus H2 divided by A1 square minus A2 square. Then speed of efflux is given by V equals to root of 2GH. So this is fluid outflow. Whenever a fluid will fall through a, say, tank, so under the action of gravity, so its speed will be root of 2GH. So when it is comparable to A, so then you will be having the areas are comparable. So then it will be root of 2GH into root of capital A square divided by capital A square minus small a square. Now time taken by water level to fall from H1 to H2, T will be equal to capital A by small a root of 2 by G into root of H1 minus root of H2. So time taken to completely empty the container by a hole at the bottom will be T proportional to root H. So put H1 equals to capital H and H2 equals to 0. So range of the liquid HR will be equal to 2 into root of small h into capital H minus h, and R max will be equal to h. So when small h is equal to h by 2. So if A naught will be equal to area of cross section of mouth of tap, so then you are having, according to Bernoulli's theorem, V naught square by 2 plus GH will be equal to V1 square by 2. So now Reynolds number NR will be equal to rho Vd divided by eta. So it will be equal to inertial force divided by viscous force. So here it is the dimensionless number and it will determine the flow of the fluid. So here if the flow is streamlined, if NR is less than 2000, if it is less than 3000, greater than 3000, then it is turbulent. If it is lying between 2000 and 3000, then the flow is unstable. And then we are having a critical velocity, the velocity above which the fluid flow is turbulent and below which the fluid flow will be streamlined. Now surface tension, the force of attraction between similar molecules is known as cohesive force, and the force of attraction between the dissimilar molecules is called as adhesive force. So now here what will happen is the free surface of a liquid will try to behave as if it is in a tension, and this property of a liquid due to which it behaves like a stretched membrane is called as surface tension. So because of surface tension, the liquid will try to occupy the minimum surface area. So surface tension will be defined as force per unit length of an imaginary line. And then we are having surface energy, the potential energy stored per unit area in liquid surface of a liquid is known as surface energy. The unit as joule per meter square or erg per centimeter square. Surface tension is given by T equals to W divided by delta A, that is work done to increase the unit surface area is equal to the measure of surface tension. So surface energy is T times surface area. Surface energy will be equal to T into 4 pi r square for a liquid drop, and for a bubble, so it will be 2 times T into 4 pi r square. Angle of contact is the angle between solid surface inside the liquid and the tangent onto the liquid surface at a point of contact. It depends on a relative cohesive and adhesive force of solid liquid phase and temperature. So application of surface tension. So we are having a drop of radius capital R breaks up into n identical drops. The work done will be equal to change in surface energy. So it will be n into 4 pi r square minus 4 pi capital R square into T. So this is the formula which we have used in order to solve many numericals in surface tension topic. So here capital R cube will be equal to small n into small r cube. So work done will be equal to 4 pi r square T. into n to the power 1 by 3 minus 1. So n identical drops coalesce to form a single drop. So heat produced will be equal to 4 pi r square heat n to the power 1 by 3 minus 1, which is equal to mc delta theta, where c is the specific heat capacity, m is the mass, which is equal to 4 by 3 pi r cube into rho, and delta theta is the change in temperature. A needle floats on a surface of liquid due to surface tension. Surface tension decreases with rise in temperature. The surface tension decreases by adding sparingly soluble impurities like detergents, and surface tension increases by adding soluble impurities like NaCl and sugar. So these are the important points related to the surface tension, which should be kept in mind while solving the numericals. Now, excess pressure inside a liquid drop, soap bubble, and air bubble can be calculated. So Pi will be equal to P naught plus 2T by R, Pi minus P naught equals to 4T by R, and Pi is equal to P naught plus 2T by R. So these are the different equations for excess pressure inside a soap bubble, liquid drop, and air bubble. Next, capillary tube, concave meniscus. So you are having Pi equals to P naught minus 2T by R, and Fa is greater than Fc by root 2. Similarly, convex meniscus, you will be having Pi minus Pi equals to P naught plus 2T by R. So Fa is less than Fc by root 2. So combining of bubbles, when two or more bubbles coalesce in vacuum, then P naught will be 0. So R square will be equal to R1 square plus R2 square. So if two soap bubbles come in contact to form a double bubble, then R equals to radius of interface R1 greater than R2, 1 by R equals to 1 by R2 minus 1 by R1. The interface will be convex outward towards larger bubble and concave towards a small bubble, because P2 is greater than P1 greater than P0. Now, capillary action, we can see if the angle of contact is less than 90 degrees, then it will be concave meniscus, and if it is greater than 90 degrees, it will be convex meniscus. So then ascent formula, height formula, h will be equal to 2t divided by rho gr, or 2t cos theta divided by rho rg. So this is the equation for a height of a capillary inside a capillary tube. So then some important points related to it. So it will be, if theta, t, and rho is constant, then h is inversely proportional to r, or h into capital R will be equal to constant. And mass of the liquid rise is proportional to small r. So h is greater than equal to 0 for concave meniscus, that is rise. Then h is less than 0 for convex meniscus, that is fall. For water glass interface, theta is equal to 0, that is meniscus is nearly hemispherical. And then for mercury glass interface, theta is 135 degree. So two capillary tubes of radius R1 and R2 are joined to form a U-tube opened at both ends. So this U-tube is filled with water. The level in the two limbs will not be same due to capillary action. So H will be equal to 2T cos theta divided by rho g, that is difference in level, into R2 minus R1 divided by R1 R2. So liquid in tube of lower radius will be at a higher level. So this is all about your fluids. Now coming to the concept of viscosity. The property of a liquid by virtue of which it opposes the relative motion between its adjacent layers is known as viscosity. So fluid friction is due to viscosity, and fluid in contact with the plate is moving with velocity v, whereas at the free end it will be moving with highest velocity. So viscous force is given in this case by F equals to minus eta A dV by dy, where eta is the coefficient of viscosity, dV by dy is the velocity gradient, and A is the surface area. So units of coefficient of viscosity is poise, so Pascal second. So 1 Pascal second is equals to 10 poise, 1 decapoise. So CGS it is 1 poise, so it is 1 dyne per centimeter square second. So this is how we are having the units of viscosity. Coming to Stokes law, when a small spherical body of radius r is moving with velocity v through a perfectly homogeneous medium having coefficient of viscosity eta, then it experiences a retarding force given by F equals to 6 pi eta rv. So now here eta is the coefficient of viscosity, r is the radius of the spherical body, v is the velocity, and it is the maximum velocity with which a body will travel in a fluid, and hence it is called as the terminal velocity. So here sigma is the density of the body and rho is the density of the liquid. Next, coming to the terminal velocity equation, so it is the maximum velocity with which an object will move in a fluid. So maximum velocity in a fluid, you call it as terminal velocity. So it will be 2 by 9 into r square g by eta, rho minus rho naught. So where rho is the density of the sphere and material, and rho naught is the density of the liquid. So the velocity increases from 0 to Vt, and then it becomes constant. Then it decreases from 0 to Vt, and then it becomes constant. So this is how the equations will be. With increase in temperature, the water, eta decreases, terminal velocity increases, and when sigma is less than rho, the body will move upward with the same terminal speed. When water is replaced by glycerin, terminal speed decreases. So this is how we are having the equations related to the terminal velocity. So this is all about your fluids chapter. Thank you.